In this lesson, we're studying rational functions. Our primary focus for this lesson will be in learning the characteristics of a rational function that will aid us in sketching its graph. The first part of the lesson will be geared more for the college algebra student, but there will be a couple of topics that we'll do at the end of this lesson that are aimed primarily for our pre-calculus students. In order for us to start our lesson, I want us to look first at the definition of a rational function so we'll understand what type of function we're studying in this lesson. Rational functions are quotients or ratios of polynomial functions. For example, here the rational function that I'm going to call r of x is equal to some polynomial function p of x divided by another polynomial function which I'm going to call q of x. And of course, as any time when we do a division, we want to ensure that our denominator is not 0 when we divide. So this definition of a rational function will be good for any values of x that do not make our denominator become 0. Now, this will sometimes be important for us also. If p of x and q of x have no common factors, then r is said to be in lowest terms. Now, that definition is much like the definition that you see with fractions, isn't it? And in fact, that's what our rational function is going to look like, is a fraction. But in this fraction, the numerator and denominator will consist of polynomial type functions rather than just numbers. Now, the first thing that we're going to do in this lesson is concentrate on finding domain and intercepts for some of these rational functions. You're going to find out that this idea of domain is extremely important for us with rational functions, and also intercepts are always pretty much easy points to find, and they are points of interest a lot of times for us. So let's talk first of all about domain. Recall that the domain is the set of all replacements for our independent variable. In this equation, y equals 2 divided by x plus 3. This is in our usual format that we see functions written. We could have said f of x here instead of y, but that doesn't make any difference in terms of this being a function. But what we're interested in is, with this equation and looking at our equation, can we determine the acceptable replacements for the variable x? And of course, the important thing for us, just as we mentioned a moment ago in the definition, is that whenever we have a fraction or a quotient, our denominator cannot be 0. So we know in looking at this function right here that it is not permissible to let x equal negative 3. The reason that is not permissible is because negative 3 plus 3 would give us a 0 denominator. So we're saying here that our denominator cannot equal 0. I'm going to abbreviate that. Denominator cannot equal 0. So if we take our denominator and set it equal to 0 and solve for x, this x value makes the denominator become 0. So this x value is not allowed. And so what we're going to do here to write our domain of our function is we're going to say all reals except negative 3. Now, another way of writing that, if you prefer, is just to make the statement x cannot be negative 3. And we'll keep that in mind. Of course, you can also use interval notation to write this domain. We're not going to get into that at this particular moment. The important thing for us to recognize is that we cannot use negative 3 in this equation. Now, in terms of a graph, the reason that that's important for me is if x cannot equal negative 3, then I will not have a point graphed for x equals negative 3. There will be no graph at x equals negative 3. Now, the second thing we're asked to find here are the intercepts. Recall we want to find both the x and the y intercepts. Let's review that concept. If we want to find the y-intercept, what do? We let x equal 0, don't we? So to find the y-intercept, we're going to let x equal 0 in our equation. Well, looking at our equation, if we substitute a 0 for x, our equation would read y equals 2 over 0 plus 3, or simply 2/3. So whenever x is 0, y is 2/3, and this gives us our y-intercept. Now, to find x-intercepts, what do? To find x-intercept, we let y equal 0. Now, let's take a look at our equation. If I let y equal 0, my equation will read 0 equals 2 over x plus 3. Now, I'm going to show you with this the long way, but then I'm going to shorten this and give you a quick way of determining this x-intercept. Recall that when you have an equation that involves fractions, you can multiply both sides of your equation by the common denominator. Our common denominator, since 0 could be written over 1, is x plus 3. Now, notice on the left, x plus 3 times 0 still gives me 0, doesn't it? And on the right, the x plus 3 is going to cancel out, and all I have left is a 2. Well, of course, we can see 0 does not equal 2, does it? This is false. And so what does that tell me? That tells me if I let y be 0, I get no solution for x. There is no solution here. So there is no x-intercept for this graph. Now, the long way of working this out is once you've put 0 over here to multiply both sides of the equation by your common denominator, get your resulting equation and see if there's a solution. But I want to remind you that with fractions, there's only one way that a fraction can equal 0, and that's if the numerator is 0. Remember, if you have 0 over 2 or 0 over 5 or 0 over -1 or whatever, all of these fractions simply are equal to the number 0. We know we cannot have a denominator of 0, can we? So if we have 0 is equal to a fraction, it is the numerator of the fraction that must equal the 0. So with these rational functions, when we're finding x-intercepts, by letting y be 0, we're going to get 0 equals a fraction, and all we'll need to do is look at the numerator part of that fraction and see if it can equal 0. If it cannot, we'll have no x-intercept. If it can, then we will have found that x-intercept. Well, let's look at another example where we're finding just domain and intercepts here. This particular rational function is y equals x minus 7 divided by x squared plus x minus 6. Now, let's work on this domain first. Remember, what we're interested in here is because we have this fraction format, this quotient, we do not want our denominator to become 0. So what we're going to do is take the denominator, x squared plus x minus 6, and set it equal to 0 to see what values of x would make it become 0. Now, if you'll notice here, of course, what I have is what? It's a quadratic equation, isn't it? How do we solve a quadratic equation once it's in this standard form? Don't we factor over here? Our factors for this particular polynomial are x plus 3 times x minus 2. And so once we have those factors, we'll set each factor equal to 0, and then we'll solve for x. Of course, we get x equals -3 and x equals +2. Now, these are the two x values that will make x squared plus x minus 6 become 0. So these are the two x values that I may not use. So for our domain, I'm going to say over here that x cannot be -3, and I'm just going to put a comma and put a 2. X cannot be -3, x cannot be 2. Now, a lot of times, rather than writing this over as a separate equation, one thing I like to do is just to take my original function over here and factor the denominator if it's not already factored. And so if I do that over here, then it's easy for me to see that if I let x be -3, I will get a 0 times something, which I cannot do. Or if I let x be 2, then I get a 0 times something, which I cannot do in this denominator. So this might be a quicker way, and I'll probably do this in the future when we're looking for our domain. If we can factor our denominator, we're going to do that, and then we can easily see the values of x that will make that denominator become 0, and we can exclude those from our domain. Now recall, again, what this is telling me is that there will be no graph at -3 for x or at +2 for x, because at those two values of x, this function is not defined. Okay? Now, let's get intercepts. Let's go ahead and find the y-intercept first by letting x equal 0. So we're going to choose x to be 0. Well, look at your equation over here. If you let x be 0 in the numerator, 0 subtract 7 is -7, isn't it? In the denominator, if the x's here and here are both zeros, then I have 0 plus 0 subtract 6 is -6. So y will become +7, 6. So if x is 0, y is 7, 6. There's my y-intercept. Now, to get the x-intercept, recall, we're going to choose y to be 0. And again, remember, if we set 0 equal to a fraction, I'm going to go ahead and put it down right now. I'm going to put it in this factored form. You could do like you did a while ago, multiply both sides by the common denominator. Notice on the left, the denominator times 0 would still be 0. The denominator times this part on the right would cancel, and we'd just be left with x minus 7. So I'm reminding you again that instead of writing this, what I'm going to do in the future is simply, when I let y be 0, here I'm going to know that if my fraction is 0, it is this numerator that must be equal to 0. So if my numerator of x minus 7 is 0, then I can easily solve for x here, and x is 7. So whenever x is 7, y is 0, and I have my x-intercept. Here's another example where we're finding domain and intercepts. Now I'm going to do this one like we did a moment ago. I'm going to rewrite my rational function here, because I notice that my denominator, again, will factor, won't it? That's a difference of squares. So our factors are x plus 1 times x minus 1. Now, can you look at those factors and tell me what are the x values that you may not use in this function? What happens to this factor if x is -1? We get 0, don't we? 0 times anything else is 0. So x cannot be -1. What about our second factor? What value of x would make that factor become 0? It would be +1, wouldn't it? So I have, again, two excluded values for x. X cannot be +1 or -1. And again, that means there's no graph for those two particular x values. Now, let's go ahead and get our y-intercept by letting x be 0. Notice in your equation, if x is 0, 3 times 0 is still 0. Subtract 2, so my numerator is -2. And in the denominator, 0 squared is still 0. 0 subtract 1 is -1. So my y-intercept is +2. I go through the point 0, 2. Okay? Now, remember what we're going to do on x-intercept. We're choosing y to be 0. If y is 0, my fraction is 0, what do? It's the numerator that must be 0. So 0 would equal my numerator of 3x minus 2. And now we'll solve for x. Let's add 2. And then, of course, divide by 3. And so our x-coordinate is 2/3. My x-intercept is 2/3, 0. Are you beginning to get the idea of what we're doing here? Notice for the domain, we're looking for those values of x that would make the denominator become 0. To find the y-intercept, we simply substitute 0 for x and solve for y. For the x-intercept, we substitute 0 for y, and what that amounts to then is the numerator equals 0, and we solve for any x value that might give us. I have one more of these problems where we're looking simply for domain and intercepts. Now in this rational function that I have here, I notice that both the numerator and the denominator can be factored. Did you notice that? Let's rewrite our function and let's go ahead and factor both of these. What are the factors up there in the numerator? X plus 4 times x minus 3. Did everybody see that? And then notice in the denominator, I just have a common factor of x in these two terms. So I'm going to factor out x, which leaves 3x minus 2. Okay? Now, let's talk about domain first. Remember, I'm looking for any value of x that will make this denominator become 0. We'll look at your first factor right here of x. Of course, if x is 0, then we get a 0 down here, don't we? So x cannot be 0. What about from this factor? Can you determine if you set this second factor equal to 0 and you solve for x? You'd add 2, then divide by 3, so x would be positive 2/3. So x cannot be 0 because of this factor. X cannot be 2/3 because of this factor. I have two excluded values. Now, to get the y-intercept, it's probably easier, because we're substituting a 0 for x, to go back to the original problem and take a look. Well, notice right away what I just said. To find the y-intercept, we substitute a what for x? 0. Well, if you didn't catch it here, look up here. If we substitute a 0 for x, we get a negative 12 over what? 0. So we just said right here, x can't be 0, can it? So what does that mean here? That means there will be no y-intercept. I can't let x be 0 in this particular problem. Now, to get x-intercepts, we're going to choose y to be 0. And again, remember, if we let y be 0, it's the what? The numerator that must be the 0. That's one reason I wanted to factor that numerator a while ago. If the numerator is 0, and I already have this factored, then it's obvious that x is either what? Negative 4 or positive 3. So I have two x-intercepts, negative 4, 0, and positive 3, 0. Now, we've been working on finding these intercepts and looking at the domain, and you'll see in a moment when we go to our graphs why we're so interested in finding those values. Now, I want to start this lesson in terms of graphing by using the very most basic rational function that we have, and it's a graph that you're already familiar with, but I want to talk about some of its characteristics and how that will carry over for us. This says to graph f of x equals 1 over x. Well, you probably learned that as the reciprocal function, perhaps, okay? But I want to talk about this graph. Let's notice, first of all, for my domain, what can I not use for x? I can't use 0, can I, because of that denominator. Now, because I can't use 0, I will have no y-intercept because I can't let x be 0. Then my next question is, what about an x-intercept? Well, remember, f of x is just like saying y, isn't it? This is just like writing y equals 1 over x. So if I let y be 0, and we've already said with a fraction equal to 0, it is the numerator, which is 1. Is this true? That can't happen, can it? So there is no x-intercept either. Now, having no y-intercept or no x-intercept tells me that my graph will never cross either the x or the y-axis. Now, let's review a little bit in terms of just picking some values of x. Remember, if x is 1, 1 over 1 is 1. So whenever x is 1, so is y. If x is 2, 1 over 2 is 1/2 for y. If x is 3, I get what? 1/3. And remember, the farther out this direction that I go, I'm going to get 1 over 10, 1 over 20, 1 over 30, 1 over 100. I will always have some positive value for y. It will be very small. Recall that this graph comes down and gets very, very close to the x-axis, but it never quite touches the x-axis because y can't be 0. Y can't be 0 here because that would not make sense for my function. Okay? Now remember, we also chose some fractional values for x, like 1/2. If you have 1 over 1/2, you get 2, don't you? And 1 over 1/10 is 10. Recall that this part of the graph went up and got very, very close to the y-axis. But again, notice we're not going to touch that y-axis because x can't be 0. And if we touch that y-axis, we're letting x be 0, aren't we? Now also recall we can choose negative values for x. If x is -1, 1 over -1 is -1. If x is -2, 1 over -2 is -1/2. I'm graphing that point. -3 gives me -1/3, and so forth. Again, my graph gets very close to the x-axis but doesn't touch it. Using a fraction like -1/2, we get -2, and so forth. And again, our graph will touch or get very close to the y-axis but not touch it. So my graph looks something like this. I had 2 branches. We sometimes refer to these as branches. But the important concept that I wanted to talk about right here was the fact that this graph has asymptotes. You should learn to spell that word, asymptotes, asymptotes. Now, the y-axis is called a vertical asymptote. Now, what's happening at a vertical asymptote? Well, you'll notice that for this particular graph, on the left-hand side of my vertical asymptote, my graph is going down, down, down. It's like my y-values are getting large in absolute value, but they're negative. Okay? On the right-hand side of my asymptote, my y-values are getting very large in a positive direction, aren't they? So sometimes we will make this statement. As x approaches 0, and I'm going to put a little negative sign after the 0. Now, how we read that is x approaches 0 from the left. That little negative sign up there is saying from the left. Now, the way I like to remember this is by putting the 0 first and then putting this negative. That's like we're taking a little bit away from 0, so that puts us on the left-hand side of 0. As x, this approaches means gets very close. As x gets very close to 0 on the left-hand side, what is my y-values doing? My y-values are getting very big in a negative direction. Big in absolute value is what I mean there. So we will say, as x approaches 0 from the left, y is approaching negative infinity. Infinity just means it keeps getting bigger and bigger and bigger, of course, in the negative direction. Now, let's look at this statement. As x approaches 0, this time I'm going to put a little plus sign on that. That means from the right-hand side, 0 plus a little bit more. So you're on the right-hand side of 0. Well, on the right-hand side of 0, but very close to 0, what are my y-values doing? They're increasing in a positive direction. So y is approaching positive infinity. Okay? Now, basically, this is what we mean by a vertical asymptote. Okay? I'm going to write the word vertical up here. If you have a vertical asymptote at a certain value of x, in this case it just happened to be 0, then on either the left or the right, or perhaps sometimes it'll be doing the same thing, I'll show you some of those, but you will either be approaching positive or negative infinity. Your function will either just start going way, way up or way, way down like this. Okay? So we'll be talking about vertical asymptotes in a minute, giving this formal definition and how we find those. Now, this graph also has what we call a horizontal asymptote. On the horizontal asymptote, notice as we let x increase in size, we're going out to the right on our x-axis. X is getting bigger and bigger and bigger. So I'm going to say it like this. As x approaches positive infinity, what is y doing? Well, let's talk about our y-values. As I keep going way out to the right, my y-values keep coming down a little bit lower and lower, and they're getting close to the x-axis, which means they're getting close to 0. Now, Notice I'm not putting an equal sign here. I'm not saying y equals 0 because it can't. But I'm just saying as x keeps getting bigger and bigger and bigger, y is getting very close to 0. We read that approaches means getting close to. Notice also as x approaches negative infinity. Now what does this mean? Well, negative on the x-axis is this direction. So I'm getting very big in absolute value, but I'm going in a negative direction. As I go out this direction for my x values, what are my y values doing? Well, notice again they're doing what? They're getting closer to that x-axis, meaning they're getting closer to a y value of 0. Notice they're just coming in toward that from underneath it rather than from on top. Okay? Now, you will find that with rational functions, we very often have vertical and horizontal asymptotes. Now, not every time. We're going to try to look at a variety of problems. But what we want to do now is to look at a formal definition for vertical and horizontal asymptotes and also talk about how we find those asymptotes. Okay? First, we're going to look at vertical asymptotes. The line x equals a is a vertical asymptote of the graph y equals f of x if y approaches infinity or y approaches negative infinity as x approaches a from the right or x approaches a from the left. Now this is exactly what we were talking about in that last problem. As we get close to a certain x value, which we're calling a here, doesn't matter if we're on the right or the left, but what matters is what's y doing. Is it getting very big in a positive or a negative direction? If so, then we have a vertical asymptote. Recall x equals a is the equation of a vertical line through the value a. Now, for us, this is important. To find vertical asymptotes, find the values of x that make the denominator 0 but do not make the numerator 0. I want to underline that do not right there. A lot of students stop with this first part. They find the values of x that make the denominator 0, but they forget to check this second part. And there's really a reason that sometimes they do that. Usually in our college algebra courses, we don't see very many functions where we will get a 0 in the numerator as well. But in pre-calculus, we're going to see that. So I really want you to start learning right now in college algebra that to find the vertical asymptotes, you do look for the values of x that make the denominator 0, but then you also check to see if those make the numerator 0 also. So I'll be doing that on this tape, even though we won't run into problems like that until the very end of the tape. Okay? And I'll be reminding you again of what this rule says. Now, horizontal asymptotes. The line y equals b, notice this is a horizontal line, isn't it? The line y equals b is a horizontal asymptote of the graph, y equals f of x, if y is getting close to b, y approaches b, as x approaches either positive infinity or negative infinity. So this is saying as x goes to the right on my graph or to the left on my graph, getting bigger and bigger in absolute value, is my y value getting closer and closer to some designated value? If it is, then I have a horizontal asymptote there. Now, to find horizontal asymptotes, we divide the numerator and denominator by the highest power of x in the denominator. Let me underline that part. Divide the numerator and denominator by the highest power of x in the denominator. I'll be illustrating with a problem here exactly how we do this process and why it works. Now, at this point, what I'm hoping that you're beginning to see, we're going to be interested in finding our domain, and we're going to be interested in finding our intercepts. The next thing we're going to look at are, do we have vertical and horizontal asymptotes? And then once we have all of that information, then we'll sort of put together what we know, and we may need to choose a few values of x to help us sort of finish up our graph. but you'll be surprised at how quickly we can graph very difficult rational functions. Now, I'm going to go to a problem. We'll start with one that's fairly simple, and we'll work our way up, but we're going to be going through the various steps here and finding these things that we've talked about. Now, one thing that I want to tell you right now, and I'll remind you again as we go through our problems, when you find vertical asymptotes, the first thing you look for are values of x that make the denominator 0. What does that tell you right there? Those values of x are not in the domain of the function if they make the denominator 0. Okay? And so that means we do not have a graph there. These asymptotes are not actually part of the graph. They're simply there to aid us in sketching the graph of the function. The other thing to remember is because these vertical asymptotes occur at values of x that make the function undefined and there's no graph, we cannot cross a vertical asymptote with a graph. So once you've identified where vertical asymptotes are, when you sketch the graph of that function, your graph cannot cross that vertical line. Okay? Now, it's a little bit different with horizontal asymptotes. Sometimes you will have a graph that crosses a horizontal asymptote. Now, the reason for that is, remember, horizontal asymptotes occur at values of y that we determine as we let x get very big in absolute value. So that means that for smaller values of x, that we may cross and actually touch those horizontal asymptotes. And again, I've picked a variety of problems here where you're going to see that sort of thing happening. So I'll remind you of those things as we go through some problems. Okay, well, let's go to our first example then, and we're going to graph. It says the rational function y equals x plus 2 over x minus 1. Now, the first thing I'm going to do is to list my domain. Look at your fraction here. What can x not be? Well, of course, x can't be 1, can it? Okay. Now, I'm just going to use an I here for intercepts. Okay. Can I let x be 0 in this equation? Yes, I can, because the only value I can't let x be is 1. So let's look at our function over here. If these x's are zeros, don't I just have a positive 2 over a negative 1? So my y value is 2 over negative 1 or negative 2 whenever x is 0. We can do that without much difficulty in computation. Now, let's decide, can we let y be 0? Well, if we let y be 0, remember what we're saying is that the numerator is equal to that 0. Well, we can solve this equation, can't we? If 0 equals x plus 2, then x is negative 2. So we have the intercept negative 2, 0 also. Now, let's talk about vertical asymptotes. I'm going to use a VA here for vertical asymptote. Remember, we're looking for values of x that will make the denominator 0. Well, we've already done that. X is 1, isn't it? But remember what we're going to check. Does this x value of 1 make the numerator 0? Well, no, it doesn't, because if x is 1, 1 plus 2 is 3. So 1 makes the denominator 0, but it does not make the numerator 0. So the x value of 1 gives us where our vertical asymptote is. Now you'll notice I'm writing for this vertical asymptote an equation, x equals 1. Notice in your definition of a vertical asymptote, the line x equals a. So anytime you write down a vertical asymptote, you should write it down as the equation of a line, a vertical line. So the vertical line x equals 1 is a vertical asymptote. Okay? Now, what about horizontal asymptote? Recall in our definition of horizontal asymptote, our instructions were to divide the numerator and denominator by the highest power of x in the denominator. Okay, well, let me take this equation, y equals x plus 2 over x minus 1. Now, remember, with fractions, if you have a fraction, you can divide the numerator and denominator of a fraction by the same value and have an equivalent fraction. So that's what we're doing. Notice down here in the denominator, this x to the first power is the largest power of x in the denominator. Okay? So that means I'm going to divide numerator and denominator by x to the first power. Well, let's go up here, and I'm going to write this out for emphasis this first time. This x is going to be divided by x, plus this 2 is going to be divided by x. Draw your fraction bar. This x is going to be divided by x, minus the 1 is going to be divided by x. You'll notice that we've divided everything in the numerator and denominator by x, and we chose x because that was the largest power of x down here in the denominator. Now, let's simplify this. What's x over x? It's 1, isn't it? 1 plus, I can't simplify 2 over x, so I'm going to leave that. X over x here again is 1, minus 1 over x cannot be simplified. Now, why did we do that, and how does that help us? You might be asking. Well, let's go back one more time to this definition. Remember, the horizontal asymptote occurs if we get a certain value that y is getting close to as what happens to x. X gets what? Very, very big in an absolute value, either very big positively or very big negatively, I'm going to say. Well, let's go back to this equation over here, the way I've written it. Look at this 2 divided by x. How much is 2 divided by x if x is very big, like say 1 million? Well, 2 divided by 1 million is not very big, is it? 2 divided by 10 million, that's even smaller, isn't it? What about 1 divided by a million? Or what about even if we divide by, say, negative 1 million? Well, 2 divided by negative 1 million would be a negative value, but it would be very, very small, wouldn't it? So in this form, we can see as x approaches either positive infinity or negative infinity, 2 over x gets very small, it gets close to 0. 1 over x gets very small, it gets close to 0. So these two things, since they're getting close to 0, tells us that y is getting close to 1 plus 0 over 1 minus 0. Well, 1 plus 0 over 1 minus 0 is just 1. So y equals 1 is what I'm getting here as a horizontal asymptote. What we're saying is as x approaches infinity or negative infinity, y is getting very close to 1. Now, notice it's not exact, because we're adding a little bit to 1 and subtracting a little bit because these are so small. It's very, very close to 1. But we write the equation of our asymptote as y equals 1. Okay? Now, before I do anything else, what I want to do is start locating some things on this graph. We have 2 intercepts here, 0, negative 2. 0, negative 2, I'm going to locate that point. And negative 2, 0. I'm going to locate that point, negative 2, 0. We also have learned that x can't be 1, so there's no graph there, but x equals 1 is a vertical asymptote. So right over here at x equals 1, I'm going to just put a little dotted line, vertical line here. Now this is not actually part of the graph, but that line's there to help me. Okay? I know at a vertical asymptote, my graph is either going to go way up like this or way down like this. And we're going to talk in a minute about how we can determine that. Okay? I also have a horizontal asymptote of y equals positive 1. So I'm going to dot in that horizontal line, y equals positive 1. And we know here that as x gets very big out here toward the right, our y value is going to get close to this y equals 1. Or as x goes to the left out here again, y is going to get close to this 1. Now, I mentioned to you earlier that you will never cross a vertical asymptote. I know I will not cross this line right here. But I also told you that sometimes you will cross a horizontal asymptote, and I'm going to show you now how you can determine that. Notice that your horizontal asymptote occurs whenever y equals 1. What we're going to do to see if we cross, to see if we cross the horizontal asymptote, we're going to take this y value of 1 and put it into our original equation. If y equals 1, I have 1 equals x plus 2 over x minus 1. and we're going to see if we get a solution to this equation. Notice if I multiply both sides of this equation by x minus 1, 1 times x minus 1 is x minus 1. On this side, my x minus 1 cancels, and I get x plus 2. Look at this equation. If I subtract x from both sides, my statement says negative 1 equals 2, which is a false statement, which says there's what? There's no solution, and if there's no solution, then I do not cross this horizontal asymptote. Now that's sort of good information, because over here on my graph, since I've located this vertical and horizontal asymptote, I know that my graph will not cross either one of these dotted lines that I have in here. Now, if you'll notice this part of the graph down here, I've got these 2 points that I know, and if I can't cross either of these dotted lines, I have a pretty good idea of what my graph is going to do. Can you sort of picture that? Notice as x goes to negative infinity, I have to do what? I have to get close to this horizontal asymptote. So that's sort of indicating that my graph, at least along here, would look something like this. Close to this horizontal asymptote. It's coming through this point, and then I would probably guess I'm going to come on down through this point right here, and then because this is a vertical asymptote and my graph is already sort of headed down this way, I suspect I'm going to keep coming down like this. Now I keep saying suspect, and I'm going to talk a little bit more how we can be clear about that in a moment, but I think this is what's happening over here. Now the problem is that I don't have any other points right now to know what else is happening with this graph. So I'm going to show you some things that we can do here. First of all, I want to talk about what goes on at my vertical asymptote. Okay? We're going to look at what happens as x gets, I'm sorry, I just wrote a 1 there, a 0 there instead of a 1. As x gets close to 1 from the left, remember a little negative sign on there says I'm a little bit less than 1. So on this left-hand side of 1. Now, an easy way to do this is to pick a number that is to the left of 1, just real close though, but not quite there, like 0.9. See, 0.9 is real close to x equals 1, but it's not quite there. It's a little bit on the left-hand side, isn't it? If you were to put 0.9 into this function over here for x, 0.9 plus 2 is a positive value in the numerator. 0.9 subtract 1 would be a negative value in the denominator. What happens when you divide a positive by a negative? You get a negative, don't you? So as x approaches 1 from the left, y is going to approach negative infinity. And you can see on this left-hand side, we've sort of already guessed that, and our graph is coming down like this, isn't it? Okay? Now, how did I know about this part right here? Well, I had these points, right? I know I have to get close to this horizontal asymptote here, but I also did what? Found out that I can't cross it, can I? So I know I'm not going to go above that asymptote. I can't cross it, so that tells me I have to stay right underneath that horizontal asymptote right there. Okay? Now, what can we do about the rest of the graph? Well, let me come back to this vertical asymptote a second. We talked about what happens if we approach 1 from the left. What if x approaches 1 from the right-hand side? Well, if we're on the right-hand side of 1 over here, x is a little bit bigger than 1. That would be like maybe 1.1. 1.1 plus 2 is positive. 1.1 subtract 1 is also positive. So guess what? Y is going to approach positive infinity. So on the right-hand side, my graph is going to be going up like this, okay? Approaching positive infinity, not negative infinity. Well, again, I pretty much know what has to happen then. I can't cross this vertical line and I can't cross this horizontal line, but I've got to approach this horizontal asymptote. So I'm probably going to have a sketch like this, sort of like that 1 over x looked, okay? But what we can do to be a little bit more accurate is pick a couple of x values just to be sure. So let's pick some x values on the right-hand side of this vertical asymptote. Let's just say we use x equals 2. If x is 2, 2 plus 2 is 4, and 2 minus 1 is 1. So whenever x is 2, y is 4 over 1 or 4. x 2, 1, 2, 3, 4. So I know that point right there. I might get, say, maybe one more. Let's go ahead and let x be 3. 3 plus 2 is 5. 3 minus 1 is 2. So whenever x is 1, 2, 3, 5 halves is 2 1/2. So I've got a couple points here. I've already said I'm approaching positive infinity there. And again, we've got to approach this horizontal asymptote as x gets bigger, and I can't cross it, so my graph has to be coming out like this. Now, what all is essential in doing this sort of depends on how accurate you need to be with your graphs and what your particular instructor is requiring for you. You should find your domain. You should find and graph your intercepts. You should definitely find any vertical and horizontal asymptotes. You should determine to see if you cross that horizontal asymptote or not. You can analyze to see what's happening at your vertical asymptote as you approach from both the right and left to see if you're going to positive or negative infinity. And then, assuming you have a few points, you can just go ahead and sketch things in. If you need to, you may need to pick a few values and sort of finish off the graph by doing that. Okay? Well, we spent a lot of time on that example going through in detail exactly what all we're looking for in terms of finding those asymptotes and what's happening. I'm going to try to show you as we do another example sort of a streamlined process that may speed that up for you a little bit so it won't take quite so long perhaps to do a single problem. Let's go look at another example. We are to graph y equals x divided by x squared plus x minus 6. Now the first thing that I'm going to recommend that we do is if we can factor either the numerator or the denominator, we're going to do that. And I do notice in this particular problem that we can factor the denominator. So let's write this as x divided by x plus 3 over or times x minus 2. Okay? In that factored form, then we can easily spot our domain. The values of x that we may not use are -3 and +2. So we'll list those. Let's go ahead and find our intercepts. If we choose x to be 0, notice in your original equation here you'll have 0 over -6. 0 over -6 is 0. If we let y be 0, notice if our numerator is equal to 0 over here, then x is 0. That just gives us our same point. So we only have that one point for both x and y intercepts. Vertical asymptotes. We've already selected here the values of x that make the denominator 0. We're going to do a quick check. Does -3 make the numerator 0? No, it doesn't. So x equals -3 is a vertical asymptote. Does 2 make the numerator 0? No, it doesn't. So x equals 2 is also a vertical asymptote. Now, let's check for the horizontal asymptote, and this is where I want to give you a little bit of a guideline to show you an easy way to find that. Now, I'm going to show you again one more time the long way through this, and then we're going to talk about an easy way to get there. Remember, our rule said to divide the numerator and denominator by the largest power of x in the denominator. Notice x squared is my largest power of x in the denominator. So I'm going to divide x by x squared in the numerator. In the denominator, I divide x squared by x squared plus x divided by x squared minus 6 divided by x squared. Now let's reduce these. X divided by x squared is 1 over x. X squared divided by x squared is 1. X divided by x squared is 1 over x. And then we have minus 6 over x squared. Remember the thing I'm looking for, these fraction forms that you see right here that have x in the denominator, as x gets to be a very large number, whether it's positive or negative, these fraction forms each get very close to 0. So you'll notice we have 0 over 1 plus 0 minus 0 approximately. Well, 0 over 1 is 0. So for our horizontal asymptote, we're getting y equals 0. Now, here's what I usually do instead of going through this division process that takes so long. notice my original equation says y equals x over x squared plus x minus 6. Now, my largest power of x down here is x squared. You'll notice I don't have an x squared up here in front, so I could think of this as being 0x squared plus x in the numerator, couldn't I? Over x squared plus x minus 6. Now, notice this first part right here where I have that largest power of x. My coefficient up here is 0 and my coefficient down here is 1. Notice that 0 over 1 is what we got to give us our horizontal asymptote. So what I do is, finding the largest power of x in the denominator, I look for that same power in the numerator, okay, and if it's not there, I'm going to make it happen by putting a 0 in front of that. And then those leading coefficients, I'm going to refer them there, that ratio is going to give me my horizontal asymptote, okay? So I'll show you this process again a little bit later. Basically what I've shown you here is that if I have a larger power of x down here in the denominator than what I have in the numerator, then there would be a 0 in front of that large power of x in the numerator, so 0 over any other number is 0, and I'd have y equals 0 as my horizontal asymptote. So let's make that statement, y equals 0 is my horizontal asymptote. Now, while we're here, we're going to check to see if we cross this horizontal asymptote. We check that by letting this y value that we have in our horizontal asymptote be substituted into our equation. Well, we've already talked about this. If I substitute y equals 0 in here, then it's the numerator that has to be 0, and we've already solved that. If y is 0, x is 0. So guess what? We're going to cross the horizontal asymptote at the point 0, 0. Okay? Now, let's locate our information here that we have so far. We have an intercept at 0, 0. We have a vertical asymptote at x equals -3. I know my graph will not cross that line. I also have a vertical asymptote at x equals +2. I know I will not cross that line. I have a horizontal asymptote at y equals 0. Remember, that's the same thing as the x-axis. And I already know, and I've already located that point right there, the origin, where I'm going to cross that horizontal asymptote. Now, there's a couple things very important here for me to know. My only place I cross either axis is 0, 0, and the only place I cross the horizontal asymptote is also 0, 0. So, beside that point, I will not cross any of these dotted lines anywhere else. Now, that's all the information that we have. And so one thing we might want to do right quickly is to talk about what's happening at these vertical asymptotes. Let's talk about what happens as x approaches -3 from the left-hand side. Okay? Get just on the left-hand side of -3, and you might want to think of a number like -3.1. That would just be barely on the left-hand side of -3. Look at this form of our function right here. If I put -3.1 in place of x in the numerator, my numerator will be negative. Okay? In the denominator, if I put -3.1 in this first factor, -3.1 plus 3 is going to be negative. In my second factor, -3.1 minus 2 is also negative. Now look at this configuration. If I have a negative over a negative times a negative, that's a negative over a positive, which overall gives me a negative. Since this is a vertical asymptote, I know it's going to be going either up or down. This negative sign tells me it's going to be going down, negative infinity. So on the left-hand side of my asymptote, I know my graph is coming down like this. Okay? Now, let's look at -3 on the right-hand side. Okay, so pick a number just on the right-hand side of -3. That might be -2.9. Okay? -2.9 makes my numerator negative. -2.9 plus 3 is positive. -2.9 minus 2 is negative. What happens with this configuration? I have a negative over a negative, gives me a positive. So I'm going to positive infinity. So on that right-hand side, I'm going up like that. Okay? That sort of helps to know that information already, doesn't it? Okay? Let's talk about at our second vertical asymptote of 2. We're going to approach 2 from the left. So get on the left-hand side of 2. What's a number just to the left of 2? It would be 1.9. 1.9 makes the numerator positive. 1.9 plus 3 is positive. 1.9 minus 2 is negative. I have a positive over a negative here, so that's going to be negative infinity. So on the left-hand side, I'm going down. Let's approach 2 from the right-hand side. What's a number just on the right-hand side of 2? Maybe 2.1. 2.1 makes the numerator positive. 2.1 plus 3 is positive. 2.1 minus 2 is also positive. So notice I'm getting positive infinity. So on the right-hand side, my graph is going up like that. Okay? Now, here's what I already know is happening. I can't cross this horizontal asymptote except here. I can't cross this vertical asymptote. I know my graph is coming down here. So I know my graph is going to be shaped like this over here because I'm going to be approaching my horizontal asymptote and my vertical asymptote without crossing either one of those. Now, this is where you maybe need to check with your instructor. Your instructor may just want you to sort of sketch in that shape in here, knowing that you're not going to cross your axes. Or they may prefer that you find a couple of points over here. If you need to find some points, then all you need to do is select some x values that are on the left-hand side of this vertical asymptote. So you could do something like choosing x to be negative 4. I'm going to illustrate that one for us. Let's just put our negative 4 right up here. If x is negative 4, and it really doesn't matter which of these places you want to go to, sometimes I like to go to the factors. If x is negative 4, I have negative 4 in the numerator. Negative 4 plus 3 is a negative 1 times negative 4 minus 2 is a negative 6. And so if you simplify this, you have a negative 4 over a positive 6. Well, negative 4 over positive 6 is a negative 2/3. So negative 4 gives us a negative 2/3, and we have that point right there. You can choose some other x values and substitute those in as well. And keep in mind, I also could have put it in to the original form right here. It doesn't really matter, whichever place you want to go through. I'm just going to use that one point and use what I know about my asymptotes to sketch in this part of my graph over here. Okay? Now, let's look at in between the asymptotes. I know that my graph is going up by this asymptote here, and it's coming down on this side over here, and I know I have this point right here. So I've got to be coming through this point and then coming down toward my asymptote over there. Do you see how we decided that? Okay. Do you know what's happening over here on the right-hand side of this asymptote? Notice again, we can't cross our horizontal asymptote again. We can only cross it here. So do you see that my shape is going to be like this? Again, your instructor may just let you sketch that in like that. Or again, if you want some exact points, then you need to substitute, say, x equals 3 or x equals 4 into your equation and get the exact y value that goes with that point. I want to encourage you to be sure and check with your instructor to see how accurate they're wanting you to be with these different branches of your graph. But what's important again is locating intercepts and these asymptotes. Do we cross the horizontal asymptote? What's happening at our vertical asymptotes? Are we approaching positive or negative infinity? Okay? And then do the graph in sections. If you've got more than one asymptote, work on the left of the first vertical asymptote, in between, and then on the right, and then get that graph in sections. Keep in mind, you cannot cross these vertical asymptotes with your graph. Okay, well let's graph y equals 1 over this x squared plus 4x plus 4. Again, I'm going to start by factoring my denominator. 1 over, this is x plus 2 quantity squared, isn't it? Okay? So as far as my domain is concerned, x cannot be negative 2. For intercepts, if I choose x to be 0, look at this equation, I have 1 over 4. Can I choose y to be 0? Can my numerator of 1 equal 0? No, it can't, can it? So I'll have no y-intercept. I might make a note of that. No y-intercept. I'm sorry, I'm saying that wrong. No x-intercept. No x-intercept. I can't let y be 0. So I will not cross this x-axis. Okay, vertical asymptotes. Well, -2 makes the denominator 0. Does it make the numerator 0? No, it doesn't. So x equals -2 is a vertical asymptote. What about horizontal asymptote? Remember what I was showing you a while ago? My largest power of x down here is x squared. Do I have an x squared up here? I don't have any x's up there, do I? So I can think of this as 0x squared plus 1 over x squared plus 4x plus 4. My coefficient of x squared down here is 1, so I just need that ratio 0 over 1. My horizontal asymptote is y equals 0, 0 over 1. Do I cross my horizontal asymptote? Can I let y be 0 in my equation? We've already talked about that. No, I can't. So this time I will not cross this horizontal asymptote at all. Okay? Let's locate our intercept, 0, 1/4. I have a vertical asymptote at x equals -2. And I know I have a horizontal asymptote at y equals 0. And I know I do not cross either of these dotted lines. Let's check our behavior at our vertical asymptote. Let's approach -2 from the left-hand side. Pick a number just to the left of -2, like -2.1. Look at your equation up here. The numerator is 1, which is always positive. -2.1 plus 2 would be negative, but notice what you're doing to that. You're squaring it. If you square a negative, you get a positive. So we're getting positive infinity. So on the left, our graph is going up like that. Okay. Let's approach x equals -2 from the right. Go to the right-hand side of -2 and pick a number like -1.9. Numerator of 1 is still positive. -1.9 plus 2 is positive, and if I square a positive, I get a positive. So notice there we're also getting positive infinity. On this side, we're also going up. Now, do you already know what your graph is doing? You can't cross the horizontal asymptote, and you can't cross the vertical asymptote. This part of our graph is going up, so this part has to be coming down to our horizontal asymptote, doesn't it? Right here. On this side of our graph, it's going up by that asymptote. We're going to come through this intercept 0, 1/4, and then we're going to approach our horizontal asymptote and not cross it. Okay? Again, if your instructor wants you to be a little bit more specific here, you can pick a couple of x values on either side of this asymptote and have specific points that your graph goes through. Graph y equals 3x plus 3 over 2x plus 4. Well, let's see. I can factor a 3 out of the numerator, 3 times x plus 1. And I can factor a 2 out of the denominator, 2 times x plus 2. Okay, let's talk about our domain. What can x not equal? -2, can it? Because that would make the denominator 0. Intercepts. If I choose x to be 0, look at the original form here. If these x's are zeros, then I get 3 over 4. Can I choose y to be 0? Can my 0 equal my numerator? Can 0 equal 3x plus 3? Yes, it can. And if we solve for x, x is -1, isn't it? Notice I could have seen that in this form right here. If I set this numerator equal to 0, then it's obvious -1 is my solution, isn't it? Okay? Alright, vertical asymptotes. X equals -2 makes my denominator 0, but notice it does not make my numerator 0. Horizontal asymptotes. Notice in this problem, my largest power of x in the denominator is x to the first power. I also have x to the first power on top. So I just want to look at these leading coefficients right here. 3 over 2, y equals 3 over 2 is going to be my horizontal asymptote. Remember, the reason that's happening is because if I divide by x, I get 3 here, 3 over x. If I divide by x, I get 2 here, 4 over x here. These would go to zeros, and I'd just be left with that 3 over 2. Let's see if we cross our horizontal asymptote. Now, this is going to take a little bit more work here. If y is 3 over 2 equals 3x plus 3 over 2x plus 4, to see if we can solve this, we can cross multiply here. 3 times 2x plus 4 is 6x plus 12, and 2 times 3x plus 3 is 6x plus 6. Notice when you subtract 6x, you get 12 equals 6, which is false. So there is no solution, so we will not cross this horizontal asymptote. Okay? Now let's locate our information. 0, 3/4, negative 1, 0. Vertical asymptote at x equals negative 2. Horizontal asymptote at y equals 3/2. 3/2 is 1 1/2, isn't it? So I'm going to go up to 1 1/2 and put in my horizontal asymptote. And I know I don't cross either of these asymptotes. Now, let's look at the left-hand side of our vertical asymptote. As x approaches negative 2 from the left, if I use negative, let's say 2.1, of course 3 is positive, negative 2.1 plus 1 is negative, so my numerator is negative. 2 is positive, negative 2.1 plus 2 is negative, so positive times a negative is negative. A negative over a negative is positive infinity. So on this left-hand side, we're going up. Do you know what's going to happen over here? Look at your points. You're probably coming down, but let's double check it. X approaches negative 2 from the right. Let's pick a number just to the right, like negative 1.9. Negative 1.9 plus 1 is negative, so my numerator is negative. Negative 1.9 plus 2 is positive. A negative over a positive is negative infinity. So this side is coming down. I'm going to go ahead and sketch it because I've got those points there. I'm not going to cross that horizontal asymptote, so I'm going to come up and approach that. On this part right here, I've got to approach my horizontal asymptote and not cross it. So again, I'm going to come down like this. Okay. Again, your instructor may want you to get a few specific points. So you could choose x equals negative 3 or negative 4 and get specific points that this part of your graph is going to go through. Graph y equals x squared over x squared minus x minus 6. I can factor my denominator. X minus 3 times x plus 2. So my domain, x cannot be positive 3 or negative 2. Intercepts, if I choose x to be 0, then I have 0 over negative 6 is 0. If I let y be 0, 0 equals x squared, then I get 0, 0 again. Vertical asymptotes. 3 makes the denominator 0 but not the numerator, so x equals 3 is a vertical asymptote. Negative 2 makes the denominator 0 but not the numerator, so x equals negative 2 is also a vertical asymptote. Horizontal asymptote. My largest power of x in the denominator is x squared. I also have x squared up here. What are those coefficients? 1 over 1. So y equals 1 over 1, y equals 1. Let's see if we cross. If y is a 1, 1 equals x squared over x squared minus x minus 6. If I multiply both sides by x squared minus x minus 6, 1 times x squared minus x minus 6 is x squared minus x minus 6. On the right, these cancel, and I have x squared. if I subtract x squared, I have minus x minus 6 equals 0. Add x, negative 6 equals x. So we're saying if x is negative 6, y is 1, remember. So we will cross this horizontal asymptote at negative 6, 1. Okay? Let's go ahead and plot our points that we have. We have the intercept at 0, 0, vertical asymptote at x equals 3, vertical asymptote at x equals negative 2, horizontal asymptote at y equals 1, and we know we're going to cross that horizontal asymptote at negative 6, 1. Okay, I'm going to go ahead and locate that point right there. Okay? Now, we need to decide what's happening as we approach our vertical asymptotes. Let's look at this x equals 3 first. Let's get on the left-hand side of 3. Okay, you might be thinking of the number 3. I'm sorry, I'm looking at negative 2 and saying 3. On the left-hand side of negative 2. Then we can use negative 2.1. Notice your numerator is x squared. That's always positive, isn't it? No matter what x is. So we don't need to worry about that numerator too much. Negative 2.1 minus 3 would be negative. Negative 2.1 plus 2 would also be negative. A negative times a negative down here is positive. So on the left-hand side, we're approaching positive infinity. Graph is going up like that. Let's get on the right-hand side of negative 2, and let's use negative 1.9. Numerator is still positive. Negative 1.9 minus 3 is negative. Negative 1.9 plus 2 is positive. A negative times a positive is negative. So I have a positive over a negative here. This is going to be negative infinity, coming down like this. Let's go to x equals 3. On the left, we could use 2.9. Numerator's positive because it's squared. 2.9 minus 3 is negative. 2.9 plus 2 is positive. A negative times a positive is negative. So I have a negative infinity again on this side. On the right-hand side of 3, I could use 3.1. Numerator still positive. 3.1 minus 3 is positive. 3.1 plus 2 is positive. Everything's positive. So I'm getting a positive infinity. Graph is going up like that. Okay, are you getting used to sort of analyzing what's happening at these asymptotes like that? Okay, now let's talk a little bit about these different sections. I know my graph is approaching up this vertical asymptote here, and I know I've got this point negative 6, 1 right here. Well, I want us to do one little check right quick. Once we go to the left of x equals negative 6, let's see where we are. So I want to substitute negative 7 into my function. Okay? Well, let's see. Negative 7 squared would be a positive 49. Negative 7 minus 3 is negative 10. Negative 7 plus 2 is negative 5. So I have 49 over positive 50, 49 50ths. The thing I wanted you to notice is 49 50ths is just a little bit less than 1. So at negative 7, my graph is below 1. So that tells me I have come across that horizontal asymptote. But keep in mind, because I have that horizontal asymptote, my graph is not going to come way down here, but it's going to stay close to that horizontal asymptote. It's just going to be underneath it. So my graph has crossed my horizontal asymptote, but it's still going to approach it and be very close to it. It will just be underneath it instead of being on top of it, like some of the other graphs that we've seen. So it was very important for us to know about that point right there. Now, in between our vertical asymptotes, I think you can see with these two sides going down like this, and you have this point. Remember, this point right here is the only place that you can cross your x or y axis. So we have to be coming up to that point and then coming back down on this other side over here. We can't go across and come back, or we would have had another x-intercept somewhere, which we didn't have. That's our only intercept right there. And then on the right-hand side of this vertical asymptote, we know we're approaching positive infinity here. Again, we know we're not going to cross this horizontal asymptote anywhere but this one point we've already found. So this part of our graph has to be coming down to our asymptote like this. Again, you may need to find a point or two to satisfy your instructor here to be a little bit more accurate with that part of the graph. Well, let's see, let's graph 2x squared over x squared plus 4. I can't factor this denominator, can I? Can't factor a sum of squares. Well, let's talk about my domain then. I can't factor this, so what I'm looking for is what value of x will make this denominator become 0. Well, there's not anything, is there? If I square a number and add 4, I can never get 0, can I? So my domain is going to be all reals. There's no excluded values here. Okay? Let's talk about intercepts. If I choose x to be 0, I get 0 over 4 is 0. And of course, if I let y be 0, 0 equals 2x squared. If 0 equals 2x squared, what's x? 0 again, right? So I only have the one intercept at 0, 0. What about vertical asymptotes for this graph? Well, guess what? I don't have any. Why don't I have any? Because there's no value of x that makes the denominator 0. There's not one. What about a horizontal asymptote? Well, notice my largest power of x down here is x squared. I also have x squared up here. What are those coefficients? 2 and 1. So y equals 2 over 1. Y equals 2. Let's see if we cross that horizontal asymptote. If we let y be 2 in our equation, 2 equals 2x squared over x squared plus 4. I'm going to multiply both sides by x squared plus 4. So I have 2x squared plus 8. These cancel, equals 2x squared. If I subtract 2x squared, I get 8 equals 0. There's no solution, so I do not cross this horizontal asymptote. Do not cross. Well, this is going to be an interesting looking problem. Let's see, we've got this intercept at 0, 0. We have a horizontal asymptote at y equals 2. No vertical asymptotes, and I know I don't cross this line right here. Well, I think on this one we're going to have to find a few points to see if we can get some idea of what's going to happen here. I might want to remind you a little bit, it's probably been a while since you've thought about it, but let's talk about symmetry. What would happen if we change x to negative x in this equation? Would it make any difference? Do you see all of the x's are squared? So since changing x to negative x makes no difference, we have symmetry to this y-axis, so whatever happens over here is going to be mirror image over here. Let's choose a couple of x values. We already know what happens at x equals 0. Let's look at what happens at x equals 1. If x is a 1, 2 times 1 squared is 2. 1 squared plus 4 is 5. I get 2/5. Notice if x is negative 1, I also get 2/5, don't I? Okay, so 1 gives me 2/5. Negative 1 also gives me 2/5. Well, let's try 2 here. If x is 2, 2 squared is 4 times 2 is 8. 2 squared is 4 plus 4 is 8. 8 over 8 is 1. So 2 gives me 1. Does negative 2 also give me 1? Notice it'd be the same thing. Yes, it does. Do you sort of see what's happening? Let me get one more value here. Let's choose 3. 3 squared is 9 times 2 is 18. 3 squared is 9 plus 4 is 13. 18 thirteenths. Notice that is 1 and 5/13. Notice how we're still less than 2. So 1 and 5/13. Do you see what's happening on this side right here? We're going to come up, and then notice we're going to have to stay underneath that horizontal asymptote because we don't cross it. And then on the left-hand side, we're going to be doing basically the same thing, coming up underneath that horizontal asymptote, but not crossing it. Sometimes you will have to find some of these points to sort of verify exactly what's going on with these particular problems. These examples should give you a pretty good idea of how to find your domain, how to find your intercepts, how to find your vertical and horizontal asymptotes, how you determine if you cross the horizontal asymptote or not, and then using all that information, study the behavior, what happens to your y values as x approaches your vertical asymptotes on both sides, and then if you need to, pick some points to sort of fill in and make a more accurate graph. Now, if you're in college algebra, that may be all of the skills that you need for rational functions. So if that's the case, you may want to stop your tape now and just go ahead and finish this lesson. If you're in pre-calculus, then you're also going to be interested in finding slant asymptotes and also working with rational functions that are not in reduced form. So you'll want to continue on with this tape, and we're going to talk about how to find slant asymptotes, how to know when they occur, and also what you do with a rational function when you have a common factor in the numerator and denominator. So let's take a look first of all about slant asymptotes. If the degree of the numerator of a rational function is exactly 1 more than the degree of the denominator, then the function will have a slant, or sometimes we call it oblique, asymptote. To find the asymptote, perform long division and set the quotient without the remainder equal to y. Now I want to talk a little bit about this idea of slant asymptotes before we go to one of our problems. Let's take an equation like y equals 3x squared minus x plus 2, let's say, over 5x squared plus x minus 1. We have looked at some similar problems. The largest power of x down here is x squared. Notice again up here we have x squared. We've talked about taking these leading coefficients here. Y equals 3/5 gives us a horizontal asymptote. I also mentioned to you, if you had situations like this, maybe we have y equals x plus 2 over 5x squared minus x plus 1. There's x squared down here. I don't have x squared up here, so I put in a 0x squared. My leading coefficients then are 0 over 5. So I get y equals 0 for a horizontal asymptote. So in general, we find out that if the power in the denominator is either equal or larger than the power in the numerator, we get a horizontal asymptote. Of course, if the power down here is bigger, we get y equals 0. This is talking about the situation where the degree in the numerator is more. Notice it says exactly 1 more. What I want to show you with this analysis here, let's suppose I had 3x squared plus 2 over x minus 1. Notice here, my largest power of x down here is x to the first. If I add a term to have x squared down here, it'd be like 0x squared plus x minus 1. Look then at these powers and your leading coefficients, 3 over 0. What do you know about that? That's undefined, isn't it? Well, because like powers here would give me an undefined situation, there is no horizontal asymptote. There's not one. But what we're learning is that there might be what we call a slant asymptote. And so that's what we're going to be working with. If the power in the numerator is larger than the power in the denominator, we will not have a horizontal asymptote. If the power is, notice, exactly 1 more, then we will have a slant asymptote. Let's look at this first problem. We're to graph y equals x squared minus 1 divided by x. Now, I want to just leave it in this form right now, except I want to factor the numerator right quickly. And go ahead and talk about domain. X can't be what? Can't be 0, can it? Intercepts, well, I've already said x can't be 0. But notice, if y is 0, if 0 equals my numerator, then x could be -1 or +1. So if x is 1, I get 0 for y. If x is -1, I get 0 for y. So I have those intercepts. Do I have a vertical asymptote at x equals 0? Well, let's see. 0 makes the denominator 0, but 0 minus 1 is not 0. So yes, I do have a vertical asymptote at x equals 0. Now notice I will not have a horizontal asymptote, because if I put an x squared down here, it'd be 0x squared. I can't have something over 0. But this numerator has a power exactly 1 more than this denominator. So our rule said if that happens, we're going to perform long division. So let's take x and divide it into x squared minus 1. X will divide into x squared x times. X times x is x squared. Subtract. That drops out. Bring down the minus 1. Can you divide x into -1? No, you cannot, can you? So this is the remainder, isn't it? I might want to remind you that a lot of times you take your remainder and you write it over what you're dividing by. So we're saying y equals x squared minus 1 over x is equivalent to saying y equals x minus 1 over x. As x gets very big, as x approaches infinity, this 1 over x approaches 0. We've talked about that before, but notice we still have this x here. So as x approaches infinity, this becomes small, but y is just getting close to whatever this x value is here. So that gives us our slant asymptote. Your rule said to do the long division, then set the quotient without the remainder equal to y. The reason we're leaving off the remainder is because it tends to 0 as x gets big. So we have discovered here that our slant asymptote is y equals x. Alright, let's go to our graph. We have an intercept at 1, 0 and at -1, 0. We have a vertical asymptote at x equals 0. We know our graph does not cross a vertical asymptote. A slant asymptote of y equals x. We're going to graph this line. You should know the graph of y equals x. It goes through 0, 0, 1, 1, 2, 2, etc. So we're going to dot in that line y equals x. That's an asymptote. Now actually you can check these slant asymptotes just like you check the horizontal asymptotes. Notice you're saying y is x. If you substitute an x for y in your equation and see if there's a solution, multiply both sides by x. We get x squared over here. These cancel. X squared equals x minus 1. If you subtract x squared, you get 0 equals -1. There's no solution. So I will not cross this slant asymptote. Now, you can also do the same sort of analysis at your vertical asymptote. Let's approach 0 from the left. Let's choose on the left-hand side, say, -0.1. Okay? Well, -0.1 plus 1 is positive. -0.1 minus 1 is negative. -0.1 down here would be negative. A positive times a negative over a negative, that whole thing would be positive infinity, wouldn't it? So on the left, our graph is going to positive infinity. Let's approach 0 from the right. We could choose positive 0.1. 0.1 plus 1 is positive. 0.1 minus 1 is negative. 0.1 is positive. So this, notice, is giving us a negative infinity. So on this side, we're coming down. Okay? Now, this is sort of like what we've done before. We know the graph is going up on this asymptote. We know this point right here, so our graph is going to come down through that point. And then this is a slant asymptote that we're not going to cross, so what our graph is going to do is come down and approach that slant asymptote. Okay? Now, again, you could choose a few x values. In fact, let's do one right quick. Let's use, let's say -3. And I think I'm going to put it in right up here. Negative 3 squared is 9, minus 1 is 8 over negative 3. 8 over negative 3 is negative 2 and 2/3. So at negative 3, we're going to be down at negative 2 and 2/3. And so you can see we are getting close to this slant asymptote. On this other side, our graph is going to negative infinity on this side of our asymptote. We're going to come up through this intercept that we have, and again, then we're going to come up and approach this slant asymptote up here. Again, you may need to get a few extra points there to be a little bit more specific with that graph. Okay, well, let's look at this one. Again, my numerator will factor, so let's do that. X plus 1 times x minus 1 here over x minus 2. For my domain, x cannot be 2, can it? That would make this 0 down here. Intercepts. If I choose x to be 0, the easiest place is to look at the original. If x is 0, I have negative 1 over negative 2, which is positive 1/2. Can my y value be 0? It can it? If 0 equals this numerator, which I've got factored over here, x will be negative 1 or positive 1. So 1, 0, and negative 1, 0 are intercepts. Is 2 a vertical asymptote? Yes, it doesn't make the numerator 0, so I have a vertical asymptote at x equals 2. Notice your powers. The numerator power is exactly 1 more than the denominator, so we're going to have a slant asymptote. Well, let's do that long division here to find that slant asymptote. We're going to divide x minus 2 into x squared minus 1. Now this time I'm going to need a x place value, so I'm going to put that in right there. X squared plus 0x minus 1. X divided into x squared will go x. Now multiply x times x is x squared. X times negative 2 is a minus 2x. Subtract, that means we'll change these signs down here. Those drop out. 0 plus 2 gives me 2x. Bring down the minus 1. X will divide into 2x positive 2 times. Multiplying 2x minus 4. Subtract, we'll change those signs. Notice the x's drop, but I get 3. Will x divide into 3? No, this is my remainder, so I'll ignore that. I'll take my quotient and set it equal to y. Y equals x plus 2 is my slant asymptote. So let's write that down over here. Y equals x plus 2. Remember, we're doing the long division. We're taking just the quotient equal to y. We're ignoring the remainder. Okay, before we do anything else, let's go ahead and locate some points and things. I have 0, 1/2, 1, 0, negative 1, 0, a vertical asymptote at x equals 2, and I have a slant asymptote, y equals x plus 2. Notice this is in y equals mx plus b form. So my y-intercept is 2. I'll go to that point. Slope is 1, so I'll go up 1 to the right 1. That will tell me where my slant asymptote is. Okay. Now, let's do a quick check to see if we're going to cross that slant asymptote. Notice at the slant asymptote, y is x plus 2. So we're going to put an x plus 2 over here for y. Equals, I'm going to leave that x squared minus 1 over the x minus 2. To clear the fractions, we'll multiply both sides by x minus 2. So I have x squared minus 4. Over here, these cancel, equals x squared minus 1. Do you see what's going to happen? When you subtract x squared, you get negative 4 equals negative 1. So we will not cross our slant asymptote. Okay. Shall we look at what's happening in our vertical asymptote? As x approaches 2 from the left, we could use 1.9 for that. 1.9 plus 1 is positive. 1.9 minus 1 is positive. 1.9 minus 2 is negative. So I get a negative infinity. Let's approach 2 from the right, like 2.1. 2.1 plus 1 is positive. 2.1 minus 1 is positive. 2.1 minus 2 is positive. I have positive infinity. So be sure, let's get up here above that slant asymptote. Why am I going above that slant asymptote? Can't cross that slant asymptote. Remember, if I start down here and go up, I'm going to have to cross that slant asymptote, and I can't do that. Okay, so with these points, we've got these points, and we're coming down to our vertical asymptote. So that suggests that we're coming down here. Again, you might want to pick an x value or two to confirm that we're doing this. And on this side, if I'm going to go up by this vertical asymptote and I can't cross this, I'm probably going to have a shape like this. Let's get 1 or 2 points here just to be a little bit more accurate. Let's see, let's choose x equals 3. I think I'll put it in here. 3 squared minus 1, that's 9 minus 1 is 8. 3 minus 1, I'm sorry, 3 minus 2 is 1. So when x is 3, I get 8. 2, 4, 6, 7, that would be about right in there. So really need to be a little bit farther up right there. And let's try 4. 16 minus 1 is 15. 4 minus 2 is 2. 15 halves is 7 and a half. So when x is 4, 1, 2, 3, 4, 5, 6, 7 and a half. I'm a little bit farther down than I was on that 8. So you can see we're coming here, and then again we're going to come up and approach that slant asymptote. Okay? I have one more slant asymptote problem that we're going to look at. We're to graph y equals x squared plus 1 over 1 minus x. Now notice on this one I cannot factor the numerator. Let's talk about domain. What can x not be? X can't be 1, can it? Intercepts, if x is 0, then I have 1 over 1. Okay. Can I have y equals 0? Can 0 equal this numerator, x squared plus 1? There's no solution there, is there? So, cannot have y equals 0. Do I have a vertical asymptote at x equals 1? 1 makes the denominator 0, but it does not make the numerator, so x equal 1 is a vertical asymptote. Notice the largest power of x down here is first power. This is second, that's exactly 1 more. So I'm going to have a slant asymptote. We need to do our division to find that slant asymptote. Now, notice that's in the form 1 minus x, but when we divide, we need the x listed first. So let's rewrite that as negative x plus 1. And we're dividing into x squared. I'm going to put a 0x for a placeholder, plus 1. Negative x into x squared will go negative x. Multiplying, I get a positive x squared minus x. Subtract, so we'll change our signs. Those drop. 0 plus 1 is 1x. Bring down the plus 1. Negative x into x will go negative 1. Minus 1 times minus x is x. Minus 1 times 1 is a minus 1. Subtract, so change signs. X's drop. 1 plus 1 is a 2. I can't divide negative x into 2. This is my remainder, which I ignore. Set y equal to my quotient, negative x minus 1. So there's my slant asymptote. Y equals negative x minus 1. Let's go ahead and check while we're here to see if we cross this slant asymptote. Replace negative x minus 1 for y equals x squared plus 1 over 1 minus x. Notice we're going to multiply both sides by 1 minus x. Well, let's see. I think I'll just do this a quick for 1 times a negative x is a negative x. Outside product is negative 1. Inside product is a plus x squared and plus x. On the other side, those cancel, and I have x squared plus 1. Notice on this side, my minus x plus x cancels out. If I subtract x squareds, I get negative 1 equals 1. No solution. So again, I will not cross. Alright, let's find the intercept 0, 1. Vertical asymptote x equals 1. Slant asymptote. Again, this is mx plus b form. So this time my y-intercept is 0, negative 1, and my slope is negative 1. Notice. So I'll find 0, -1. If my slope is -1, I go what? Down 1 to the right 1. So this time my asymptote is slanted this direction because it has a negative slope. Okay. Let's look at what's happening at our vertical asymptote. As we approach 1 from the left, we can use 0.9. Notice this numerator, 0.9 squared plus 1, that's positive. 1 minus 0.9 is positive, so I have a positive infinity. So I'm going up on this side. As we approach 1 from the right, we can use 1.1. 1.1 squared plus 1 is positive. 1 subtract 1.1 would be negative, so I'll get a negative infinity on this side. I'm putting it down here, notice, because of that slant asymptote that I can't cross. Okay, well let's see, we've got this intercept and we know we're going up to that vertical asymptote on the left. What do you think's happening over here? Probably going to come around and approach this slant asymptote. Let's get at least one x value. Let's use -1 for x. Okay? If x is -1, when I square it I get 1 plus 1 is a 2 in the numerator. And 1 subtract -1 would be 1 plus 1 or 2 in the denominator. So -1 gives me 1. Okay? So I probably come down a little bit and then back up through that point and approach my slant asymptote like that. Okay? Now let's get, say, a point or two over here also. Let's go to x equals 2 and see what happens. 2 squared is 4 plus 1 is 5. 1 minus 2 is -1. So whenever x is 2, I get -5. 1, 2, 3, 4, 5. That's this point right here. I'm going to come down to my asymptote there. And again, we might get another point if you want to, but you're going to have to approach this slant asymptote. So it's probably going to be shaped something like that. Okay, we have one more little topic. Rational functions that are not in lowest terms have a common factor in the numerator and denominator. The graph will be almost the same as the graph of the reduced form of the function. However, you must remember to consider the domain of the original function. Now, what I want you to learn from this statement here, the graph will be almost the same as the reduced form. In fact, we're going to go to the reduced form to help us sketch the graph. What we're going to consider, though, as we do this reduced form of the function is to remember the domain of the original function. Let's take a look at an example. Graph y equals x squared minus 4 over x minus 2. I want you to notice that you can factor the numerator. X plus 2 times x minus 2. This is over x minus 2. Now our temptation is to go ahead and cancel these factors and say that's equal to x plus 2. But I want to caution you about doing that. Look at the original form of your function right here and let's talk about domain. Can x be 2? It cannot, can it? X cannot be 2. By canceling these factors, notice I have eliminated that from my realization, and if I cancel that and just look at this, I'm not going to realize x can't be 2. So that's what we're talking about remembering what that original domain is. I have to remember x can't be 2. Okay? Now I also want to point something else out here to you. Notice that 2 makes the denominator 0, but look what 2 does up here. 2 squared is 4. 4 minus 4 is also 0. Now this is the first time on this tape we've seen a situation where a number that made the denominator 0 also makes the numerator 0. So guess what? 2 is not a vertical asymptote. Remember, a vertical asymptote occurs if the denominator is 0, but the numerator is not 0. And so we don't have that here. So we have no vertical asymptotes. Okay? Now, what I want to do is talk about the reduced form. If we do cancel this, it looks like our equation says y equals x plus 2, doesn't it? Well, we know what that is. That's a line. Okay? So what we're seeing is that the graph of this original function will be almost the same as this. The only difference will be that we cannot use x equals 2. Well, let's notice in this function right here, if x is 2, 2 plus 2 is 4. We cannot have this point. Why can't we have this point? Because x can't be 2 in our original function. So basically all that does is we're going to graph this line, but we're going to eliminate this point. Well, this line is in mx plus b form. We cross the y-axis at 2. Slope is 1, so go up 1 over 1. What I'm going to do is just eliminate the point 2, 4. So let's find that point. 2, 2, 4. Let's put an open circle right there. What we're going to do is graph the line everywhere except that one little place. And we have the graph of our rational function. Just created a hole in this line. The hole was created because our original domain said x can't be 2. Okay? Let's do one more of these. Graph y equals x squared minus 5x plus 6 over x squared minus 2x minus 3. Now, I believe both the numerator and the denominator here will factor. So let's do that first. The numerator will factor into x minus 3 times x minus 2. The denominator will factor into x minus 3 times x plus 1. Do you see that common factor right there? We're going to deal with that in a minute. Let's talk about domain first. What can x not be? X can't be 3. X can't be negative 1, can it? Okay? This is my original domain that I have to pay attention to. Now, let's look at the reduced form. If we cancel those factors, our equation looks like this. Y equals x minus 2 over x plus 1. We're going to graph this function, except we're going to exclude these two values of x. Well, notice on this function, x can't be negative 1, can it? In fact, I have a vertical asymptote at x equals negative 1 because negative 1 makes this denominator 0 but not the numerator. So I have a vertical asymptote at x equals negative 1. Notice that because the powers of x are the same, I will have a horizontal asymptote. What will it be? Well, the leading coefficients here are 1s, so 1 over 1, y equals 1. Let's see if this thing crosses y equals 1. Let 1 equal x minus 2 over x plus 1. If I multiply both sides by x plus 1, I get x plus 1 equals x minus 2, don't I? Subtract x's, 1 equals negative 2. So I will not cross this because I have no solution here. Okay? What happens to this reduced form as x approaches negative 1 from the left? If I use negative 1.1, let's say. Negative 1.1 minus 2 is negative. Negative 1.1 plus 1 is negative. A negative over negative is positive. So I'm going to go to positive infinity on the left. As x approaches negative 1 from the right, I could use negative 0.9. Negative 0.9 minus 2 is negative. Negative 0.9 plus 1 is positive. So I'm getting negative infinity. Okay? Notice also, if I choose x to be 0, I get negative 2 over 1. Okay, so 0, negative 2 is my intercept. Okay, can I let y be 0 in this reduced form? Can 0 equal the numerator? Yes. If I have a 0 here, then x is 2, isn't it? So I have the point 2, 0. Okay, well let's see about graphing this stuff. I've got 0, negative 2. I have 2, 0. I have a vertical asymptote at negative 1. I have a horizontal asymptote at y equal 1 that I do not cross. I know on the left-hand side of negative 1, I'm going to positive infinity. On the right-hand side of negative 1, I'm going to negative infinity. Okay? Now, basically, I'm almost ready to graph this thing. I can see this thing's coming up like this, and this thing's coming down here. But before we graph, let's go back to our original domain. What could x not be? -1, well, that's already taken care of because of the asymptote. But look at this. X can't be 3. Well, let's look at this new equation. If x is 3, what do I get? 3 minus 2 is 1. 3 plus 1 is 4. The point 3, -4 needs to be excluded. So I'm going to find that point right quick. 1, 2, 3, 1/4. And I'm going to put an open circle there to exclude that point. Now I'm going to let this graph come on up to that little hole that we've created and then come up under my asymptote. I've got that excluded point right there. Notice over here I don't have to exclude anything, and I know my graph is going to come approach this horizontal asymptote without crossing it. So what did that common factor create? It created an excluded point at 3/1/4. Otherwise the graph is just like this reduced form. I hope that these examples has helped you to understand how to find your slant asymptotes and also what to do with those functions that have a common factor in the numerator and denominator. Generally what you're going to do is to factor and sort of think about, okay, if I cancel that factor, what does my graph look like? But then go back and you'll probably have to insert some little holes in your graph to take care of those points that were excluded by your original domain. This concludes the lesson on rational functions.